So hello, I'm Halgurd. I'm in the brain simulation section since 2 years. I will talk about one of the first projects I was involved in this team, which is about virtual brain simulations, and in particular an imaging technique known as positron emission tomography, or in short PET. You may have heard of PET scans if you have a background in medicine or related fields, or maybe like me if you have watched some seasons of Dr. House. To have an idea what it is, we can have a look into diagnostics in medicine, where PET scans are broadly used for the detection of tumors, for example. In this context, it's a comparable imaging technique to MRI, but it has some major differences in the spatial and temporal resolution of those signals. And to be precise, PET signals are usually spatially and temporally more coarse-grained. Despite this disadvantage, however, the imaging technique is very powerful, and it is used in clinical routine since it allows to track certain molecules in 3D space and in tissue, like in the human body. Let me give you an example. If I manage to change my slide, yes. Okay, so let's talk about the cerebral energy metabolism. So the energy metabolism of the brain, and in particular of the human brain. The human brain has 86 billion neurons. These neurons, they are responsible for 20% of the body's energy consumption. This percentage, by the way, it's more or less constant. It only depends little on the exact processes going on in our brain. In other words, it's a kind of a myth that hard thinking makes the brain consume more energy. However, despite the more or less constant total energy demand, there can be spatial differences in the distribution of where energy is consumed. And these spatial patterns, or let's say their alterations, can be measured using PET scans, PET scans of the brain. And they are part of diagnostic routines for neurodegenerative diseases. So what you see here is a typical PET scan of a human brain. And this is in the normal healthy brain, where you see some uptake patterns, which are more or less homogeneous across the cortex. However, with neurodegenerative diseases, these patterns can change, and they can be used to diagnose the disease. Another example is about different states of consciousness. We know, for example, that in the wakeful human brain, there's a certain level of energy consumption in certain brain regions, whereas in non-REM sleep, which is a sleep state where we don't dream, where in non-REM sleep, these patterns are changed and the brain consumes less energy. Before I give you an overview of this topic, let me make clear that what I'm presenting today is part of current research. It's ongoing research. So feel free to question specific results, because this is good practice for not yet broadly established methods like the PET model, which I'm going to talk about today. Nevertheless, a lot what you're going to see is established, and part of our daily work with brain network modeling, and in particular with the virtual brain. So in the next hour or so, I'm going to guide you through this topic and explain in detail how we can model PET signals using virtual brain simulations. So this was the intro, basically. As a second part, I will talk about what PET is, and in particular FDG PET, like what is the physics behind. Then we're going to go through how to develop a model from scratch, basically, of PET and PET signals and PET scans. What is like the foundation of this project is basically generating neural activity in the virtual brain, so simulated neural activity. For this part, I'm going to do two excursions, which I think are important to understand the details about virtual brain simulations. The first one is about dynamical system theory, and the second one is about characteristics of both signals. Both is what you measure with functional MRI. Then the model which we're going to build is, despite being built from using a bottom-up approach, it's still phenomenological, and as such, it has parameters which we cannot derive from basic biophysical principles. So there are free parameters, and we will have to tune them to make sure that our model produces plausible results. Then, as soon as we have this model established, we can study the PET response. So the response of PET signals to neural activity, just like we can characterize responses of both to neural activity. And finally, I will summarize what I've shown you today. So what is PET, and in particular 18-FDG PET? What you see here is on the right is the schematic overview of how a PET scanner works. PET scans are based on a physical phenomenon known as electron-positron annihilation, which is a reaction between matter and its corresponding and antimatter particles. So if you have a little bit of physics background, you know every particle in the standard model of physics has some antimatter counterpart, and they don't like each other so much. So when they meet, they annihilate. And in this case, the matter and antimatter particle pair is electrons and the counterpart positrons. It's basically an electron, but with a positive charge. So when electron and positron meet, they will annihilate and send out 2 photons. How does this work? How can we use this to measure brain activity? For PET scans, usually a radioactive tracer, a chemical, is injected into the subjects. The tracer spreads in the body, and the radioactive decay of this radioactive tracer produces positrons. So this is a beta plus decay, and the decay product are positrons, among other things. Well, electrons are everywhere in tissue, so the positron travels around 1 millimeter before it interacts with an electron, and when it interacts, it annihilates, and it emits 2 photons in opposite directions. The fact that the photons are emitted in opposite directions is very important because it allows us to trace back where the tracer was. So if we detect the photons on 2 sides, we can interpolate and know where the signal was coming from, where the annihilation occurred. Like this, we know where the tracer is going, and we can measure this in 3D space. And what is 18-FDG now? 18-FDG is a specific tracer. I think it's called a radiopharmacon. And 18-FDG PET is equivalent to glucose, at least for the metabolism. So it's a molecule very similar to glucose, where 1 atom was replaced by I think 18-fluor, which is radioactive and is producing these positrons. So we can inject 18-FDG PET and see where glucose is going. It means also we know where the brain is consuming energy. So what does all this have to do with brain simulations? Well, as you know, we can use different imaging modalities or measurement modalities to optimize our brain models. We can, for example, measure EEG signals, try to produce them in our models. We can measure bolt signals, so fMRI signals, and try to optimize our model. And the more of these measures we have, the better we can tune our models, and the more we can validate results, and the more robust our model becomes. Basically, for me, one of the holy grails of brain simulation is to optimize the model to produce one modality and then get the other modality for free, because this shows that our model has predictive power. So it's natural to ask if we can also implement a model in the virtual brain which resembles PET signals. And this is what the project is about. So let's try to build a PET model from scratch. We will start on the small scale and try to have something like a PET scan image at the end. And on the small scale, we will have neural activity. This is like the basic ingredient which gives rise to energy consumption and glucose uptake and so on. So what precisely do I mean with neural activity, and why does it consume energy? For this, we will have to look into how neurons behave and what consumes energy in neural activity. So let's say we take a very, very basic neuron, which reacts to some input current by emitting an action potential, a spike. This is the typical shape of a spike. You see my pointer, right? Yes. Oh, so this is an action potential. We have a depolarization during which potassium leaves the cell. Sodium leaves the cell. And we have repolarization during which potassium, I messed it up, I always confuse those. So sodium goes into the cell and potassium leaves the cell, okay? And after the repolarization, there's a hyperpolarization phase, and after this we go back to resting state. So sodium goes in, potassium goes out, and then we go back to resting state. And this whole cycle, of course, since ions go in and out, the ionic gradients are changed. The ionic gradients are very important for the spike to happen in the first place. So there must be a mechanism to restore these ionic gradients. And this mechanism is realized through pumps, which bring back out the sodium and bring back in the potassium. These are sodium-potassium pumps. Sodium out, potassium in. And this whole process, it's against the ionic gradients, so against the electric field potential. So, of course, it requires some energy to move the molecules, the ions against the gradients. And in fact, it consumes ATP. This is the basic energy units in the body. Since it consumes ATP, somehow we have to redeliver ATP into the cell. So somehow this whole procedure of ATP consumption triggers a so-called hunger signal, which then makes it possible that glucose is uptaken by the tissue in order to deliver more ATP. Okay, so this is why neural activity consumes energy to maintain and restore ionic gradients. So we have, this is a schematic model of a neuron. This is a neuron, this is axon, this is some other connection. And this neuron has some ATP and neural activity consumes this ATP. Then we have, in fact, the glia cells, which trigger this hunger signal, which I mentioned. And this hunger signal allows the blood vessel to release glucose and increase the ATP concentration again. Okay, so neural activity causes ATP consumption, causes a hunger signal, causes glucose uptake, and finally an increase of the ATP concentration. Where does the FDG-PET signal come from now? As I said before, FDG-PET is more or less equivalent to for the body as glucose. So when the tissue uptakes glucose, it also uptakes FDG, 18-FDG. And the detector knows where this 18-FDG is because it's doing this positron electron annihilation. So this is what gives us a PET signal. Okay, all very complicated, but we can just summarize this into one block of our pipeline, which is the neurogliovascular and PET model. Neurogliovascular, there are three terms in this: neuro for neuron, glio for glia cells, and in particular astrocyte, as we will see in a bit, and vascular for the blood system and blood vessels. Okay, so this is all very detailed. We have to summarize this somehow. In summary, the PET signal is proportional to the glucose uptake, which in itself is proportional to the ATP concentration. And now, in order to model this, we just need a mathematical description for this. And we looked into the literature. This is always the first thing you should do. Maybe someone has modeled this already, and it's true, someone has modeled this already. There are detailed biophysical models which have hundreds and more equations. This one particular example has 89 dimensions, so it's a dynamical system with 89 equations, trying to model all the signaling pathways of glucose metabolism and energy metabolism. So I will try to go through this briefly because it's quite complicated and we will not use it in the end, but just to give you an idea. So here we have the neuron. This is the sodium-potassium ATPase pump. This is where the energy is consumed, and this is what restores and maintains the ionic gradients. The ATP consumption triggers a hunger signal. This is this cryptical symbol here stands for the hunger signal, which is transferred to the astrocytes, which after all cause the capillaries to release glucose, which is transformed to lactate and pyruvate, which enters the cell and through complicated transformation become ATP, which is then being used by the pump. So all very complicated. But since we want to use this in brain simulation, we have to somehow simplify this. We cannot model every single neuron in brain simulations using 89-dimensional dynamical system. So we have to simplify this and somehow try to capture the main effects which are in action during neural activity. So what happens in summary? We can say that at each spike somehow ATP is consumed, where at the same time each spike also causes some sort of hunger signal or a production signal to make sure that there's always enough supply of ATP. And at rest, we know that the ATP and the production signal, they should somehow recover to baseline. This is, of course, a very simplified version of what happens in real, but maybe it's enough. With this simplification, we can describe this mathematically quite easily in two equations. It's these two equations. I will explain it. So A represents the ATP concentration. It's in absence of activity, it will just decay to 0. This is this first term. At the same time, it increases with F. With F, where F is some production signal, and it also decreases with firing activity. This R represents the firing rate. The second equation describes the dynamics of the production signal, which also at rest decays to 0. Not at rest, but in absence of firing, it decays to 0. And it increases with firing. So A decreases with firing and increases with F, but F increases with firing. So somehow there's an interplay of ATP concentration decrease through firing and ATP increase through this production signal. One thing to mention is maybe that the fact that this production signal, it's bounded. It has an upper bound, so there cannot be infinite supply of ATP. Okay, of course, this model has parameters. These are these 3 parameters, and we will see later how to choose these parameters. So let's put this back into our overview. We have this module, which stands for the neurogliovascular and PET model. The input to this block is basically neural activity. And the output is ATP concentration, which we know the PET response will be proportional to. I have skipped a little bit of detail on the left side of this pipeline, where we have the neural activity. This neural activity, we of course cannot access the neural activity of arbitrary brain regions to large detail using imaging. So in this situation, we will use the virtual brain simulations to produce this raw neural activity. So simulating neural activity in the virtual brain. How does this work? You have seen this probably before. The starting point of every TVB simulation is some neural mass model, so a model which can produce neural activity and somehow mimics the behavior of large populations of neurons. We can couple these neural masses together to model their interactions using empirical data of how brain regions are connected, so a structural connectivity, which is just simply a matrix telling us how nodes are connected. And this is already what we need to perform whole brain simulations. So these whole brain simulations, they give us neural activity. And I will spend a few minutes on this part already, because I think there's a lot happening under the hood. And I will tell you what is exactly happening in my first excursion about dynamical systems theory. So how do we precisely generate neural activity in the virtual brain? We need a neural mass model, as I said. And one neural mass model which is often used as a first start is a generic 2D oscillator. I will explain what it is. It's a dynamical system with 2 equations. It has some index variable, which is k. This is the region index. So k tells us which brain region we're in. It has variable v, which is some sort of average voltage variable. I say in quotation because this is a phenomenological model, so it's not an actual average. Then we have some recovery variable. This recovery variable models the slow recovery after depolarization of during an action potential. And it has certain properties as generic to the oscillator. First, it's a phenomenological model. It's nevertheless powerful for the following reasons, namely because it exhibits typical properties of neuronal dynamics, for example, multistability, oscillatory behavior, dynamics on multiple timescales, and a few other things. And for those of you who are maybe familiar with this, it can be seen as a generalization of Fitz-Nagumo type models or Maurice-Lécar type models. This is why it's called a generic 2D oscillator. So if you choose the parameters accordingly, you can get a Fitz-Nagumo model, basically. Okay, so despite the fact that this system has only two equations, it's a complex model. It is highly nonlinear, and it's important to understand such a complex model. But how can we do this? We have to simplify it. We cannot just simulate, we cannot just take the full model with many brain regions and coupling and structural connectivity from empirical data if we want to understand this model. So we have to simplify it somehow. And the first obvious simplification is to reduce the whole problem to one region. So instead of having the index k, we can just look at a single isolated region. Then we notice that there is a parameter in this model, which is the external current. Before reducing this to a single region, this external current is time dependent. Now, since it's a single region, the external current is not time dependent anymore because nodes do not receive network input. And typically you will find a parameter like this in neural mass models. So there's one in the generic 2D oscillator, but there's also external current parameters in other models. And I posed the question, or we posed the question, which states can a single region reach given a constant value of this external current? The answer to this can be obtained performing so-called bifurcation analysis. So basically, we want to find stable states and attractors given a constant value of the external current. And we want to find parameter values at which qualitative changes of these attractors occur. Sounds all very complicated, but I can explain it in more detail. So you see the equations on the right side. We have the voltage variable and the recovery variable W, so V and W. We can look at this problem in the so-called phase portrait, where we have, I'm not sure if you can see it, because now I can see it. We have voltage on the x-axis, and we have the recovery variable on the on the y-axis. Here on the top right, you see the current parameter which we are at. This is this external current, which is right now 0. These arrows and lines, they point in the direction of the flow of the system. So they indicate in which direction solutions of this dynamical system will go when we start them somewhere. Let's say we start our system here, then we will follow this line here, okay? And you can see that all those lines, they are spiraling into some region here, this red dot. This is a so-called fixed point. This is a so-called fixed point. And the color code here shows you that the more blue these lines are, the slower they move, and the more yellow they are, the faster they move. So the color code corresponds to the speed of these trajectories. So this red dot is a fixed point, and in fact, it's a so-called focus. So we have not only an approach towards this fixed point, but we have a spiraling approach. And the location of this fixed point, it depends on the parameter. So if we increase the parameter, this fixed point is moving. And at some point, At some point, we get a second object, which is this orange circle, which is a limit cycle. So this is a stable limit cycle, and now the fixed point in the middle is not stable anymore, but unstable. So it's not attracting anymore, but it's repelling. So if we start inside this orange circle, we will be attracted towards the orange circle. We will be repulsed from the fixed point here and attracted towards the limit cycle. And from the outside as well, we will be attracted to the limit cycle. So we have a stable attractor here, which corresponds to oscillatory behavior. So as we change the parameter, we get a limit cycle, which changes its shape. When we increase the parameter further, then the limit cycle shrinks again, and we will end up in a fixed point again. Now, this is an animation, but we can represent this in 3D space, where we put W and V on two of the axes, and we put I on the third axis. This looks like this. So it's the same animation, and on the right now you see this fixed point moving, and then we see the limit cycles. And then the limit cycle disappears again. Okay. Why am I telling you all this? What does this have to do with PET? Well, if we have such a model like the generic 2D oscillator and we want to perform brain simulations, it's useful to know and to be able to anticipate how the system behaves without performing complicated simulations. And this is what bifurcation analysis allows us to do. To give you a better intuition of how to read this diagram in 3D space, I can show you this animation where we simulate several generic 2D oscillators, 20 or so of them. Each of them is uncoupled, but they have different parameters, like different external current parameters, from 0 to around 15. And we just start simulations of these uncoupled nodes and see what happens. And we can see that they start and they approach the attractors, which we know through the bifurcation analysis. All right. And we can also see that there's some slow recovery ongoing because the trajectories which are oscillating, they have a part where they move very fast and they have a part where they move very slow. And you can also see that the frequency of the oscillations is different depending on the parameter. And when there's no limit cycle, the nodes simply approach the fixed point, this white line here. So this is how to read these 3D bifurcation diagrams. Okay. So this is bifurcation analysis. We find the attractors of the model depending on the bifurcation parameter, which usually is the external current. There's only one problem, which I have hidden from you. Usually in brain network models, the external current is not constant. So this whole approach only works if the external current is constant. In the case of brain network simulations, each region receives long-range coupling, LRC. So the external current is time-dependent. It usually consists of some constant component plus the long-range coupling and plus noise if you have noise in your model. So this is now the input current, which is now time-dependent, and it's region-specific. So how can we possibly use this? How can we possibly use a bifurcation diagram where this is all easier to understand the network simulations? So we have the constant offset and this long-range coupling, which is usually excitatory. I can show you very roughly how it looks like, this long-range coupling. It has global coupling scaling parameters. So the whole coupling, the whole long-range coupling which the system receives, which a single node receives, is scaled by this parameter G. Then it has this CKL term, which is the structural connectivity from empirical data, and this VJ term, which is just the state of the other regions. And we can perform an actual brain simulation, not bifurcation analysis, but an actual brain simulation, and see how the external current behaves. So this is now a brain network simulation where the nodes are coupled, not the uncoupled, but they are coupled. And we see the state variable V of each node, we see the state variable W of each node, and we see the external current to each node. This is just an example. It works for other parameter setups. And in this case, the constant offset of the external current is 5, and the global coupling is 0. So what this means is that the external current is just constant in time because there's no global coupling. It's just the constant offset. But as we increase global coupling, the external current starts to fluctuate. So each node receives a different input now, which is changing in time. The color code here color codes the node degree, so how much input according to the structural connectivity a node receives. And as we increase the global coupling further, we see that nodes start to synchronize and the fluctuations of the external current become larger. I can go back to some intermediate value of coupling and check what happens when we not change the global coupling, but the constant offset, so along this axis here. And we see that when we change the constant offset, obviously it just shifts the whole curve of currents here. Okay, so in brain network simulations, the external current is not constant. Nevertheless, we can see that at least for intermediate global coupling values, it oscillates around some value, around the constant offset. We can try to. We have these three time series, V, W, and I external. We can try to still draw this on the bifurcation diagram of this single isolated node and see if we can use this to understand what's happening in the network. So on the right side, now you see, why am I in time, by the way? It's okay. On the right side, you see the bifurcation diagram again of the generic 2D oscillator. And now this blue disk here are the trajectories of the network simulation. We see V, W, and I external current as the coordinates in this space. And we can perform the same, let's say, parameter exploration. First, we increase G. And then we can see that the nodes of the network's simulation, somehow they spread along this bifurcation diagram from left to right, from low external current to high external current. Let me pause it here. And we can also see that the nodes with low degree, they are more on the left of this diagram. And the nodes with large degree, they are more on the right of this diagram. That makes sense because nodes with large degree receive more input. So the external current on average is larger for those nodes which have high degree. So what we see here is when we increase G, the whole distribution of nodes along the parameter of the external current becomes wider. Whereas if we change the offset, the whole thing, the whole family of trajectories moves left and right. Okay. So this is, of course, just an approximation. Like the bifurcation diagram is, of course, just an approximation of the network behavior. The bifurcation diagram is the bifurcation diagram of a single node, so we cannot expect the network trajectories to perfectly follow the structures which we see in the bifurcation diagram. Nevertheless, we can see that the oscillations which we observe in the brain network simulation, where the nodes are coupled, are associated with the limit cycles of the uncoupled system. Okay, now this was a very long excursion, but you will see later why this is very useful. For now, we can get back to our pipeline to simulate PET. So to recap, we have a neural mass model, we have a structural connectivity. Together, they represent our whole brain simulation model, which produces neural activity based on some dynamical system and based on some neural mass model. This neural activity, of course, if we don't infuse it with empirical data, it's not very meaningful. As you see, this is like what you get when you just simulate the generic 2D oscillator, you get something sinusoidal. What we want is plausible physiological neural activity. And to do this, we have to use data. The data which we use is already here on the left side, the structural connectivity is already empirical data, but somehow we have to make sure that the neural activity time series is as well meaningful. For this, we use MRI data, in particular functional MRI data. So we can perform some optimization of of our simulation in order to reproduce empirical data. And when this optimization is done, our neural activity will have some meaning, because the neural activity is what produces the fMRI data. Okay. There's something in the chat. Okay. This optimization is quite important, and I will spend a little bit more time explaining how it precisely works. Just a second. So, as you maybe know, with the virtual brain, we can not only produce neural activity, but we can also monitor measures which we usually obtain empirically, for example, bolt signals and fMRI signals. And this is my second excursion about the characteristics of bolt. Bolt is, again, the signal which you measure in fMRI. I hope I'm not saying obvious things here, but just to be sure that we're all on the same level. So characteristics of bolt. What you usually see, or what you see very often, is so-called bolt functional connectivity. What is it? We take the bolt time series of each brain region, simulated as well as empirical, and we compute Pearson's correlation between different brain regions. So the matrix entry FCKL is simply given by the Pearson correlation of the time series of region K and the time series of region L. So if the two regions would be fully synchronized, the Pearson correlation is 1. If they're in antiphase, the Pearson correlation is -1. Okay, so this is one of the main characteristics of bolts, which we try our simulation to reproduce. Second thing, what about other characteristics? For example, synchrony. We can also take into account synchrony. We can take the starting point, the bolt time series of brain region K. We can compute phases of each of these time series for each region using a Hilbert transform. And we can compute from these phases the so-called Kuramoto order parameter. This is the equation of it. What is important is that this is a complex valued number, but we can compute the modulus of it. And if this modulus is 0, the system is fully desynchronized, fully disordered. And if the Kuramoto order parameter, or the modulus of it, is 1, the system is fully synchronized. We can do this computation for the empirical bolt time series and for the simulated bolt time series. And we can try to adjust the parameters of our simulation such that the synchrony level in both is the same. So this is an example of an already fitted simulation. On the left side, you will see the empirical time series, not of bolt, but already of the synchrony measure. And on the right, you see the simulated one. On the bottom, you see the average phase of the signal, and also the average synchrony, which is the length of this line here. As I said, it's a complex valid number, so we can compute the angle and the length of the vector. And you can see the empirical data has a certain level of synchrony. The simulated data starts out very synchronized, and then it reaches also a certain level of synchrony. And we try to match these levels of synchrony, the simulated to the empirical one, to make sure that synchronization is taken into account in our brain network model. Okay. I don't know why it's running again. Doesn't matter. Okay, finally, what about brain dynamics? Because the bolt functional connectivity, it's a static measure. We don't have a time series anymore, which we can investigate. The synchrony as well is a static measure. We look at the average synchrony. We look at with the FC, we look at the average interactions between brain regions and the Pearson correlation. But what about the dynamics of these? For the dynamics of bolt signals, we can compute what is called functional connectivity dynamics, FCD, which works in the following way. Instead sorry, instead of taking the whole time series to compute our FC, you can just take a time window to compute our FC. So we can have a sliding time window in which we compute the functional connectivity matrix, and then we can compare the matrix at different times. So this is a bold time series of some average subject. We can divide this into time windows. For example, this is the time window T0. We can compute the FC in this time window. We can see how the FC changes as a function of time. So this is, we see already how the FC changes dynamically. And we can create a second time window. This blue one, and as well compute the FC, the functional connectivity for this time window. Of course, they will differ because they are measured at different times, and somehow the dynamics, the brain dynamics show different structures, even in resting state. So we compare these two FCs at the different time windows, computing correlation again. So in this case, the correlation between time window T0 and time window T120 is 0.14. And then we can put this measure, this new correlation, into a new matrix by scanning these two time windows against each other. And slowly build up a picture, which is called the functional connectivity dynamics matrix, the FCD matrix. Which contains information about how likely it is that brain states reoccur. So this is the final functional connectivity dynamics measure. Essentially, what the color code means is that if you pick a time point on the x-axis, let's, for example, pick 570 on the x-axis, time point k, and you pick a time value on the y-axis, let's say 570 again, then this one pixel here represents the correlation of the FCs of the functional structure at this, the correlation between the FC at these two time windows. So of course, if you compare 570 against 570, it corresponds to the same time window and the correlation is large. When you move to the right now, you compare time window 570 to a little bit later. So the FC is still similar, you have still bright pixels, but it's already less similar. And when you're far away from the diagonal, you will get much lower values, but you still see some sort of block structure. For example, here, this brighter block here, it means that the state at time, 1050 or so, was similar to the state at, let's say, 600. Okay, so this is functional connectivity dynamics. And from this functional connectivity dynamics matrix, we take the upper triangle, this upper triangle, and we compute the distribution of correlations. In this case, we know that states reoccur with a Pearson correlation of around 0.3. Okay, so this is the last characteristic of Bold, which I will speak about. Of course, you can do even more elaborate things, but these are the three which we took into account for this project. So we have a FCD matrix from which we compute this distribution. So to recap, we have static functional connectivity, we have synchrony, and we have functional connectivity dynamics taken into account for our optimization of the model. Next, we actually optimize these parameters. We actually optimize our model to match the empirical data. For this, we need data. And it would be nice to have a data set which contains bold as well as PET, because we will have to also fit our PET model later. And we found a data set which contains this. This is a data set from the Monash University in Australia. And for now, we will focus on the MRI data of this data set. So bold fMRI of 60 minutes. So we have bold signals per brain region for 60 minutes. And from these bold signals, we can compute all these measures, FC, synchrony, and FC dynamics, and we can compare them to our simulation. So what you see on the top right is how well the simulation with a given parameter combination fits the how well a simulation with a given parameter combination fits the empirical data. Here you see the synchrony, here you see the FC dynamics. So this is kind of a brute force optimization where we do a grid search using parameters of the model, which in this case is global coupling and the external current, the constant component, which you have seen before of the generic 2D oscillator. And what you see in this big panel is a combined measure. So it's a weighted sum of the FC fit, the synchrony fit, and the FC dynamics fit. Okay, and we see more or less bright pixels here. The brighter, the more yellow the pixel is, the better we're fitting these measures. This is an animation in this parameter space. This trace here, just to make this clear, this trace here has nothing to do with the fitting. The fitting is simply picking the brightest pixel in this grid search. I'm just drawing by hand the trajectory here to illustrate how certain regions of this grid search look like. For example, this point, we can see that the FC of the simulated data doesn't look very plausible. We can see that the FCD distribution, the distribution computed from the FCD dynamics matrix, FC dynamics matrix, is a little bit shifted compared to the empirical data. And yeah, synchrony is not so bad, but the other measures are not good. So this is how we perform the fitting of our TVB simulation to match empirical data. Here you can see the system is overly synchronized, for example. And where is it? Looking for a specific point, I think I missed it. Just to give you an example, here we see that the correlation between FCs, the empirical FC and the simulated FC is not too bad. It's a correlation of 0.33, but the FCD distribution looks awful compared to the empirical data. So this is why we try to combine different measures. First of all, it prevents overfitting, and secondly, it improves the plausibility of our TVB simulation. And this is finally the point where like the parameters give the best fit to all those measures. Okay, so we have a TVB simulation which was optimized to produce plausible simulated Bolt signals. And at this point, we can at least to some extent claim that the raw neural activity, which is the basis of the Bolt signal which our simulation creates, is also plausible. So we can use this optimized neural activity here as some sort of ground truth. Okay, so this is our block for the TVB and TVB neural activity and fMRI simulation. We have a structural connectivity, we have a neural mass model. Both together make up a brain simulation which produces raw neural activity. We can use a Bolt model to simulate, to get Bolt signals from the raw neural activity, and then we can optimize the simulation in a loop. Okay, let's put this into perspective of our whole pipeline. We have our neurogliovascular and PET model, which takes neural activity and outputs a PET response. And we have a block which produces neural activity. So we can use this neural activity which we produce from the optimized TVB simulation to plug it into our PET model. Okay, and the PET model will output something. But as I said before, the PET model has parameters which needs to be tuned as well. For this, we need PET data. And we can look back into the data set and this part of the presentation, which is about the PET model optimization and validation. We can look back into the data set, which contains also PET time series. So before we were only using the Bolt time series, now we can have a look into the PET time series and perform optimization of all model parameters. So this is again the PET model. It has these three parameters, tau f, f increase, and a decay. And the optimization of these parameters works as follows. We take the empirical PET time series from the data set, so a time series per brain region. And we take the simulated PET time series, which we set equal to the ATP concentration of our PET model. As we have seen before, the PET signal is proportional to the glucose uptake, which is proportional to the ATP concentration. So the simulated PET time series is produced by the PET model block, and here used to compute, used as a simulated PET time series. These are time series. We want a simpler measure to tune our model. So we compute a static PET, which is basically the total signal of each brain region. So it's the integral of the time series in each region. So it's one, in the end, we have one value per brain region. And we compute this, and we compute the static PET for the empirical data and for the simulated data. And we optimize the parameters such that the simulated PET corresponds as good as possible to the empirical PET. So how do we perform this fitting? We used a genetic algorithm, which is an iterative approach to optimize parameters based on evolution theory. Probably you know about it. And we have used this genetic algorithm only on 3 subjects. Why? Because we don't want to overfit our data. We don't want to fit all the subjects at once, because obviously if we fit all the subjects at once, we don't have subjects remaining to validate our model with. So we use it only on 3 subjects. And you can see here how the parameters change over the iterations of the fitting algorithm until they reach some plateau where the fitness, the goodness of the fit is not increasing anymore. And these final parameters we take as parameters for our PET model. How do we validate this? I will show you group averages of the empirical static PET image computed from the empirical data and of the simulated data using these optimized parameters. And here at the bottom, you can see that the group average static PET of the empirical data correlates 0.56 with the simulated data. That's not so bad. That's quite good, in fact, given that it's the average data. Though this is validation number 1, the simulated data resembles very well the empirical data. Second validation, we wondered what determines how good our PET model, our PET simulation explains the PET empirical data. And our first intuition was to check whether or not it matters how good we fitted the bold simulation in the first place. As you know, in the pipeline, there's first a block with TVB producing raw neural activity, which is fitted to bold. And it's natural to ask whether or not it matters how well we fit bold for the PET model. So we can, for now, just focus on the orange block here and this orange line. This orange line tells us the better we fit bold, the better we fit our TVB simulation to produce empirical bold signals, the better our PET model performs. This makes sense, because the better we fit bold, the more plausible the raw neural activity time series is, and the more plausible the output of the PET model is. Secondly, we also compared whether or not we can simply use the bold model, which already exists in TVB, to explain the PET data, and it doesn't seem to work. So the bold activity does not correlate too well with the PET signal. We also wondered if we can just take the mean neural activity. Maybe we don't need a complicated PET model to explain the data. Maybe we can just take into account the mean neural activity directly produced by our neural mass model to explain the PET data. But it works less good than the PET model. Okay, third validation. As I said before, the PET, the data set contains not only static PET images, but PET time series. And as for bold, we can compute functional connectivity matrix from these PET time series. So this is now not fMRI functional connectivity, but PET functional connectivity. And we can, again, perform this computation of the functional connectivity for the empirical data and for the simulated data and compare them against each other. And we find that they correlate well with each other. So on the left, you see the empirical PET functional connectivity. On the right, you see the simulated PET functional connectivity. So in this case, we have not even tried to optimize the model, the PET model, for producing this. It just comes for free, even though we only have optimized our model to reproduce static PET images. Okay, so let me come back to the overview, and I think that's a good moment maybe to take a little break. Yeah, I think it's a good moment to take a little break. Maybe 10 minutes. Leon, what do you say? What do you think?
It depends on your schedule, I think.
I think I'm good with 10 minutes.
Okay.
Okay. And yeah, maybe after the break we can have a little chat about if someone has questions. So I see you back at 5:40. It's good?
Okay.
Okay, cool.
Yeah, then.
Let's stop this recording. So welcome back. I will recap where we are. We are trying to develop a model which captures PET signals of empirical data. And there are 3 blocks in the whole pipeline. The first one is the TVB simulation, which creates raw neural activity and bold signals, which are tuned to resemble empirical data. The optimized raw neural activity is then being used as an input for the second block, which is the neurogliovascular and PET model. It takes neural activity, in this case from TVB, and outputs a PET response. And the third block, the model, the PET model itself, is fitted on a subset of the empirical data to resemble static PET images. So now we have an optimized model which produces plausible static PET. What can we do with this to gain insight? Let's have a look at the PET model block, the optimized one. And let's try to study the PET response characteristics. So what does the PET response depend on? When is it high? When is it low? And for this, we can just, for a moment, ignore TVB simulations and just input artificial signals into the PET model. First, let's take transient input, and to be precise, a simple Gaussian pulse with a specific amplitude. So this is the input on the top panel. For comparison, we see the bold response, like the fMRI response based on the recent model in TVB of bold. And on the last one, we see the PET response of the optimized PET model. So on the bold response has this typical shape where we get one peak at the activity, and after the activity, the input activity, we get a little dip, a negative peak, and then we go back to its base value. Whereas in the PET response, we just have one peak. This is for small input. How about when we increase the amplitude of the input? Then we can see that the bold response, as we go from small input to intermediate input to large input, the bold response just scales up. So the shape stays the same. We have one peak followed by a negative peak and then going back to rest. What about the PET response? Well, it seems like the PET response is changing shape depending on the amplitude. For intermediate input, we get this little dip in the main peak. And for very large input, we get even a negative peak. This change of shape is related to the interplay of ATP concentration and energy consumption together with the production signal. So we have amplitude dependency of the PET response. Now, what about oscillating inputs? As we know, the brain performs oscillations. This is what we measure in EEG. What about oscillating input? Let's try to take some artificial input, which is simply made out of sinusoidals with different frequency, and plug this into our bold model, which we have already in TVB, and in this new PET model. And let's start on the left side, where we have a 3 Hertz oscillating sinusoidal input. We can see the bolt response also oscillates with the same frequency, almost. And the amplitude of these oscillations decreases with increasing frequency for bolt. But the base level of the signal stays the same. Whereas for PET, we have a sensitivity to the frequency of the base level. So we have a frequency dependency of the PET response. Let me go back to this to just make sure that it's clear. For low frequency, we get a low PET response. For high frequency, we get a larger PET response. This is again related to the interplay of ATP consumption and production signal. So we have frequency dependency of PET response. Okay, we had a lot of excursions, a complicated pipeline. Let's come back to what we initially have seen, why PET is useful, and why you can apply it to different problems. So let's go back to sleep and have a look at these plots, which show the FDG, 18 FDG uptake in different states of consciousness, in awake and in so-called non-REM sleep. There's a paper from 2017 which shows that the brain's energy consumption in non-REM sleep decreases to 85% of its resting state value. So the brain in non-REM sleep consumes less energy. The NT/FDG uptake is less in non-REM sleep. Can we model this with our PET model, let's say as a final validation? How would we do this? How could we do this? Well, there's fundamental relationship of different sleep stages and spectral properties of brain oscillations. In particular, when we are awake, we have so-called alpha band activity, which is around 8 to 12 Hertz. And in non-REM sleep, we have delta band activity around 2 to 4 Hertz. So very basic idea, let's take sinusoidals and input this into our model, into our PET model. We take sinusoidals which have frequencies corresponding to the EEG spectrum, to the main components of the EEG spectrum, which are observed in awake and non-REM sleep. So for the alpha band, we take the average, which is 10 Hertz. For the non-REM sleep, we take the average, which is 3 Hertz. And we take this as an artificial input to our PET model. No TVB simulation yet. And we measure the metabolic response. How much ATP is uptaken? How much PET signal do we get? And we can see this is what we've seen before. There's a frequency dependency. So of course, the 10 Hertz signal has a larger PET response than the 3 Hertz signal. And we can compute the averages and compare them against each other to know how much is the PET response, respectively, the ATP concentration reduced when we have the 3 Hertz signal. And we can see that, surprisingly, it's very close to what was measured in this 2017 study. So when we inject the 3 Hertz frequency into our PET model, we get 87% of the energy consumption as compared to the 10 Hertz signal. And we can do, of course, a systematic analysis since it's a 2-dimensional model. It's, of course, tuned to empirical data, but it's a simple model, so we can investigate these things systematically in a very, very easy way to get insight into this. Here we can see that the PET response or the ATP concentration is sensitive to the amplitude as well as the frequency. Okay, can we confirm this in a TVB simulation? These are all artificial signals. There's nothing physiological about these sinusoidals. We should confirm this in a TVB simulation to show that this model works also in a TVB setup, and that these effects are also observed in a TVB setup where these simulations are fitted to data. So we need a model which can produce signals of different frequency. The generic 2D oscillator, which we have seen before, it can do this, but you will have to tune the parameters quite substantially, and you will never, or you will have difficulties finding a setup where the model has some sort of multi-stability between different states and can produce alpha and delta. So the model which we used instead is the Janssen-Ritt model. It has these 6 equations. I will not get into the details, but it's obviously more high-dimensional than the generic 2D oscillator, so it gives rise to more complex dynamics. And the reason it has these 6 equations is that it models multiple neural populations. There's an population of pyramidal cells, population of inhibitory interneurons and excitatory interneurons. So each of these populations is modeled by 2 equations, and then we end up with these 6 equations. Okay, what is the first step? This time, the first step will be to fit this model to data, just as we did with the generic 2D oscillator. We can perform a parameter optimization to make sure that the raw neural activity, which is produced by this model, and then fed into a bold model, produces plausible bold signals. So we come back to our measures for bold characteristics, which is FC, synchrony, and FCD, FC dynamics. So this time it's a parameter exploration in 2 parameters again, in global coupling and conduction speed. And it's the same as before. We just pick the brightest pixel here and traveling through this parameter space just to illustrate again, like that we can get completely different setups. This is not a good FC. This is not a good FCD fit. And then as we are in the brighter regions, the FC looks already a bit better. The FCD looks a little bit better. But the best parameter combination is here, where we have a compromise between FC synchrony and FC dynamics. So you can see, in fact, that the FC has a very high, the FC has a fit of 0.48, the synchrony has 0.86, and FC dynamics 0.82. Okay, so now we have a fitted Janssen-Ritt model, which produces plausible bold time series. Why are exactly these parameters the best fit to our resting state bold fMRI data? Why is this the best fit? And here is where my first excursion comes into play, the bifurcation analysis. This is the bifurcation diagram of the Janssen-Ritt model, given some basic parameter setup. It looks more complicated than the bifurcation diagram of the generic 2D oscillator because it is more complicated. We don't have only 1 class of limit cycles, these orange surfaces, but we have 2 classes of limit cycles, two families of limit cycles, sorry. We have this elongated thing, which looks like a football. This is a family of limit cycles with around 8 to 12 hertz frequency, so in the alpha band. And then we have this narrow surface with very large amplitude, which corresponds to delta band activity. Okay. To give you an idea about these frequencies, we can again simulate not a full network coupled with structural connectivity and so on and so forth, not the fitted one, but just uncoupled Janssen-Ritt nodes at different parameter values. So I distributed 200 uncoupled Janssen-Ritt models along the external current axis, just as we did for the generic 2D oscillator. And we can let these simulations of these 200 nodes run and check how the trajectories approach the attractors in the bifurcation diagram and how they move. So we start with some initial conditions, and we can see that a lot of the nodes just like maybe here, the nodes at low current, they just immediately approach the fixed point. This is how fixed points work. They oscillate a little bit around it because it's a focus. And the nodes at larger currents, they approach the limit cycles. And it takes some time for them to converge to it, but at some point they will be on it. We can see that the nodes on the, let's say, football family of limit cycles oscillate faster than those on the delta limit cycle. Of course, if the frequency along this limit cycle is high, we will see this. We see this here. One of the reasons why the nodes on the delta limit cycle have a lower frequency is because of the presence of the saddle node bifurcation. I don't have the time to go into these details, but the nodes on the delta limit cycle, they spend a lot of time on this part. As you can see, they take a long time here before they are basically ejected here and then make one round. Okay, so this is how uncoupled nodes in Janssen-Ritt behave, and we can anticipate their behavior in the bifurcation diagram. Okay. Now, how does the fitted simulation look like? We have seen this parameter exploration, the grid search of the Janssen-Ritt model. We have picked some parameters where our bold characteristics fit very well with the empirical data. Now we can again try to draw the trajectories of the network simulation into this bifurcation diagram in 3D space. And this works even better than for generic TD oscillator for specific reasons about how the coupling is realized in Janssen-Rid with the sigmoidal and so on. So this works better. And these little dots here now are the initial conditions of the network simulation, of the brain network simulation, which was fitted to the empirical data. And what we see is that all the regions, so each dot is one region, all the regions, they approach the alpha limit cycle. They're not exactly on it because the bifurcation diagram is only an approximation of the brain network model dynamics, but they're quite close to it. And we can also see that the nodes with large degree, the more yellow ones, they are more towards the large currents, whereas the blue ones are more towards the low currents. This is also consistent with our assumptions. So why is this the best fitting model? Why is this the best fitting parameter setup? Because it's the parameter setup which allows to be on the alpha band, which corresponds to physiological activity. So this parameter setup causes the Janssen model to be on the alpha band limit cycle, which is physiological resting state activity. So it's consistent. Can we put this model to non-REM sleep? Yes, we can, and we can anticipate also, and we can predict how to do this, because we know that the fitted simulation, the fitted simulation is on the alpha cycle, and we have seen for the generic TD oscillator what parameters we can change to make the whole set of regions shift towards smaller currents. We can either reduce the constant component of the current, or we can reduce the global coupling to make this distribution more narrow and at smaller currents. And this is exactly what we do. We shift the dynamics of the delta band by lowering the global coupling value. So this is now the fitted simulation, but with a lower global coupling value. And we see that it actually works if we choose the global coupling value correspondingly. And all the nodes of the brain network simulation end up, not all of them, but most of them end up on the delta limit cycle. Some of them are still on the alpha cycle, but the majority is on the delta limit cycle. Okay, so the dynamics is now dominated, when we lower G, the dynamics is dominated by delta band activity. Step 4 in this journey, we take these two simulations of the Janssen-Rid model, the one which is fitted to the empirical data with alpha band activity, and the one with lower G, where we know it's dominated by delta band activity, and we plug it into our PET model. So we take these two simulations, we plug it into our PET model, and we observe the output of the PET model, where we see clearly that the case with lower G, where most of the nodes are on the delta limit cycle, on average has a PET response which is 86% less than what we observe in the resting state. And we can compute, we can also create an image of how the PET response and the ATP concentration looks like, which resemble the reduction which we observe in the empirical data as well, from awake versus non-REM sleep. Okay, that's basically all about this topic. This is a complicated pipeline, but it ends up with a very simple model of FTG PET in the middle, which we have optimized to data. Let me give you a summary of what we have done. So as I said initially, there are many imaging modalities which we can simulate with TVB. There's EG, there's BOLD, and among other things. And the more of these modalities we have, the better we can tune our models, the more we can be sure that they have some predictive power. So now that we have added PET, the take-home message, number 1, multimodal approach, so taking into account multiple imaging modalities, including PET, allows better model validation and improves the predictive power. Then we have seen that, like the neurogliovascular system, it can be very complicated, and it's subject of current research as well to model these very complicated interactions. However, we have reduced the problem substantially to be able to use it in brain network simulation. And it works out as far as we can see. So take home message number 2. For complex problems, choose an appropriate level of biological detail. Then take home message number 3. We love bifurcation analysis because it allows a deeper understanding of a model's behavior and facilitates its exploration. I hope I could convince you about this. Little side note, this is the software we have used for all these results, and especially for the bifurcation analysis, I have used Auto 07P. It needs some practice to use this, but it has plenty of example and it's quite fast and robust. There's other software which I am not 100% familiar with. I know PyDS tools. There's also PyCobi. For MATLAB, there's MatCont. Yeah, also I can mention this here as well. For all the plotting animations, I've used Python, Matplotlib, and FFmpeg, and for the simulations, the virtual brain mainly. So last take-home message. PET is an imaging technique which is established in clinical routine. It's being used for diagnostic reasons. It's being used in basic research. It's being used in clinical research. And we have built a model which can reproduce plausible PET data. So PET is established in clinical routine. And therefore, a PET model places the virtual brain even closer to translational research. Okay, I think that's it. This is the final animation. Thanks for your attention. I'm happy to answer whatever question you have.